Hi everyone, welcome to our second lecture on synchronous machines. By the end of this session, you should be able to develop the equivalent circuit of the machine and write the equations describing it, solve for the voltages and currents using the equivalent circuit and the phasor diagram of the system, and that is something that is going to be critical to the whole process of solving for your voltages and currents, and explain the terms over-excitation and under-excitation for both generator and motor operation. So to develop the equivalent circuit, let's look again at the general construction. We have here the windings A prime, B prime, C, sorry, A prime, B prime, C and C prime. And as the electromagnet turns here, remember this is some coils of wire, so we have an electromagnet. As it turns, it cuts these conductors and it generates the voltage vectors in the coils. So essentially, if we look at into the terminals on the stator, we are going to see a voltage which was developed by this rotating magnetic field behind a reactance, because from the coils of the stator, and we are also going to see some winding resistance. So we have our terminal voltage, we have here the EMF generated by the rotating magnetic field, and here we have our synchronous parameters X, S and RS. Now in practice, for large machines, the conductor is very thick, because it's going to carry a large amount of current, so this value is very small, and we often neglect it. We consider it negligible. So what we have is just this. So this is going to be the simplified circuit that we work with, and we will see for the case of a motor that we have here. If the current is going in, we could say Vt is equal to EF, just ignore this sign, EF plus IA by XS, right? And remember XS here, this is JXS. So this is the equation describing the motor operation. And if it's generator operation, then the current is simply going to go in the next direction, and you'll have EF is equal to Vt plus Ia XS. So either way, it's very simple, a very simple equation describing the equivalent circuit. EF here is proportional to the rate of change of the field flux. Remember, the field comes from the excitation on the rotor, or it could be a permanent magnet. If it's a permanent magnet, you can't really change the strength of the field, but if it's an electromagnet, by increasing the current in the windings, you could increase the amount of flux, and therefore you could increase for the same speed, you could increase the EMF, and that is something that is very important. It's a very important concept to understand when we come to looking at how the synchronous motor operates and how we could use it to achieve things like different power factor, different levels of power factor for operation. So once again, what happens here, how we could change this, the field voltage, which is here, how we can change it is, if we go back to here, if we increase the current in this winding, if we increase it, then you're going to have more flux produced, and for the same speed you're going to have a larger rate of change of flux, which will give you a larger EF. So even though you have a voltage that may be applied to the terminals, let's say you start off applying some voltage to the terminals and you have some excitation here, you could actually increase the voltage at the excitation voltage here by increasing the the field excitation without touching the terminal voltage, and that is a very important thing, and that is one of the tricky things about the synchronous machine. It's something that brings up a lot of confusion because it's not clear. People have trouble in thinking about how could the EF vary independently of the VT, right? So it is not the case where this is, say, a passive load, so you increase the voltage here and you increase the current, and you will therefore increase the voltage across this. EF and VT are in essence independently controllable. So by controlling EF and VT, you could change the current in the winding. Now the synchronous reactance XS actually represents two things. One is the leakage flux, that is the flux not linking the rotor and stator, which is the same concept you have in your induction machine and your transformer. The second is what you call the armature reaction flux, and that is the flux produced by the induced current on the stator winding. So each one of those we could represent it as a reactance. So just to give you a little more information on the armature reaction, when the rotor field cuts the stator, an EMF is induced. So remember, the rotor is a rotating magnet. The magnetic field cuts the stator, that creates an EMF and that varying EMF will in turn create an varying magnetic field which will oppose the rotor field. So that reaction is called the armature reaction. And since it acts, as you see here, to reduce the net flux, it is in the form of an impedance, right? And specifically an inductance, because we're dealing with magnetic flux. So now we've seen the equivalent circuit, and in it there were three voltages to keep track of: the terminal voltage, the excitation voltage, and the voltage drop IAXS. We are also going to look at two angles, and we have to make an important distinction between these. One is the power angle and one is the power factor angle. The power factor angle here is exactly the same as you've done before. This is the angle between the voltage and current, the phase voltage and the phase current. And the second one, the power angle, is what tells us the amount of real power being delivered by the machine or being consumed by the machine. And you'll see this as we look at the phasor diagrams, right? And one of the other things you're going to see here that is very important is by varying EF. Remember, EF is your induced voltage, VT, EF, XS. By varying EF, which you could do by varying the field current, you could change the power factor. So let's see how that works. So first we're going to look at leading power factor. So the way you should think of this, the way you construct this diagram, is first you draw VT. VT is always on the horizontal. So first you draw VT, and then if it's a leading power factor, you know I has to be above VT. It has to lead VT by some angle theta. If so here I've just drawn it at this angle here, theta. Now IAXS, remember XS is JXS. So if I multiply IA by JXS, the resultant is going to be at 90 degrees from IA, because that is what the J does. The J shifts the angle by 90 degrees. J in phasor form is 1 angle 90. So when I multiply I by 1 angle 90, the direction changes by 90 degrees. So this IAXS, I've put it down here. So from VT down to here will give me EF. So from the equation we could see EF plus IAXS will be equal to VT. So we see here that I have my Kirchhoff's voltage law, EF plus IAXS, and it gives me that resultant of VT. So I have here my power factor angle. The angle made between VT, which is the terminal voltage, and EF, which is the induced voltage, is what we call the power angle, right? And you'll see here that the power angle, as we'll see in a little while, tells us the amount of power being produced by the machine. Notice also for the power factor, this angle here is the same as this angle here. Now what determines this angle here? As I reduce the angle theta here as it comes this way, right, then this vector is going to go from here to, let's say, here to here, and if I is perfectly in line, it will eventually be straight. If I is vertical, then IAXS will be like this, right? IAXS will be here, and theta would be 0. So the way I could change that is by changing the magnitude here of EF. So if I change the magnitude of EF while keeping this angle constant, eventually I could change this theta to 0 and then change it from leading to lagging. So that is what we're going to look at in the next couple of slides. So this is for the leading power factor. For unity power factor, IA and VT are in phase. IAXS will be here. So I have EF, and then I start my IAXS here at the end of EF, and it should meet back at VT. So in this case, I have the power factor angle is 0. And for the lagging power factor, again, here's my line, right? I'm going to have the power factor angle being negative. So so just by varying the value of EF here, I could control the direction of the current and the angle between the voltage and current and the power factor, right? So this is for, of course, VT is equal to EF plus IAXS. If I draw my circuit diagram from that, if we want to figure out if it's for a motor or a generator, I have EF plus IAXS VT. So if I'm adding the voltages this way, it means the current has to come this way, which would mean it is a motor, the current going in from the electrical side to the mechanical side, right? So let's look at the real power now, and you know power is VI cosine theta. For 3 phases, 3 VI cosine theta. What I want to do is I want to represent this not in terms of theta, but in terms of the power angle delta. So I'm going to look for a relationship here that I could use to equate theta with delta. So from my diagram, I see here this is IAXS. So if I make a right angle out of it, a right angle triangle, and then I could say IAXS cosine theta will give me this value here, this length here. And this length is the same length as if I look at EF from here. If I make a triangle like this, so this is my triangle here now. Let me take off this line. If I look at this triangle here now, it is the same length as this line here. So the 2 dotted lines we're trying to equate. So this dotted line from this triangle is IAXS cosine theta, and then this triangle here, this dotted line, is EF sine delta. EF is the hypotenuse in this case. So EF sine delta. Now I could say, I could take I cosine theta and substitute it here, and I could substitute that I cosine theta for EF sine delta on XS, and I will get the power then as 3 VT on XS multiplied by EF sine delta. And these are, of course, phase values, right? Normally, if you get a question, the question specifies the line-to-line voltages. You have to convert that to the phase values if you want to use the 3 VTEF. These are all phase values. This is a phasor diagram with phase voltages on it. So that is the real power. And then for the reactive power, I know reactive power is 3 VI sine theta. So again, I'm going to go here and look at IAXS sine theta, which will in this case give me this part here of the triangle, and I want to equate it to this part here. So IAXS, which is this diagonal here, multiplied by sine delta gives me this, and then EF by cosine, IAXS sine theta gives me this, IAXS sine theta, and now this entire thing here is EF cosine delta, but I only want this portion here, so I'm going to subtract VT, and it will get rid of this part here, and I will remain with here. So that is what I have, EF cosine delta minus VT. And then again I substitute IA sine delta here for EF cosine delta, IA sine theta for EF cosine delta minus VT on XS, and I end up with this equation here. So to summarize, I have the power, the real power, being equal to 3 VT on XS EF sine delta, and the reactive power being related to cosine delta. Right? Now don't confuse this with the power factor angle. The power factor angle is the angle between the terminal voltage, the terminal phase voltage, and the terminal phase current. The power angle is the angle between the terminal voltage and the induced voltage, EF and VT. Right? So one of them tells you the amount of power, the other one tells you the displacement between the voltage and current. So how could we tell that the machine is motoring or in generator mode? If we look at the phase diagram and so on, how would you know if it's being operated as a motor or as a generator? So if EF is greater than VT, remember this is our phasor diagram here. So if EF is greater than VT, then the current might go this way, and we'll say, well, it's a generator. And EF less than VT, then the current might go the other way, and you'll say, oh, okay, that's a motor. But that is actually, wrong. It has nothing to do with the magnitudes of EF and VT. Right? If you go back to our slides on leading and lagging power factor and so on, you'll see that you could vary EF and VT independently. So the thing that we have to look at here is actually the power angle. A positive power angle means you're generating, and a negative power angle means you're motoring. Now what is the reason for this? So we have two things. Remember, the power angle is the angle between VT and EF. Now VT is the voltage from the electrical system, and this one comes from the mechanical system, from the rotation of the magnetic field. So if EF is ahead of VT, it means that the mechanical system is pulling along the electrical system. So if the mechanical system is pulling along the electrical system, then you will have a generator, because for the generator you supply the mechanical power, and that starts pulling the electrical system. When I say pulling, I mean it figuratively. It starts pulling along the electrical system so that you get this electrical the sinusoid on the electrical system. And if you supply the electrical energy, then you get your rotating magnetic field, and that pulls along the rotor. So here what we're looking at is the lead and lag of the rotor field to the stator field. So the phi rotor to the phi stator. If the phi rotor is ahead, right, which is the mechanical system, it means that it is a generator, and if the stator is ahead, it means it is a motor, right? So this is what we discuss here, so that you could review it, and to move on and see how this looks, you'll see that for your circuit diagram here, which is motoring, right, the current going into the from the electrical to the mechanical side, you'll see that you could have, depending on the power factor, you could have variations in the length of EF. Well, you could actually set EF to give you different power factors. So if it's a motor, you could draw a variable, you could make the machine operate as a variable power factor load by adjusting EF. Now when the power factor is leading, we call it overexcited, which is when EF is greater than VT. Well, not really when EF, when the projection of EF onto VT is greater than VT. And we call it underexcited when the projection of EF onto VT is less than VT, right? So for the motor, underexcited corresponds to a lagging power factor, and overexcited corresponds to a leading power factor. For generating, we have the opposite. When it's generating, we have a positive angle here, and the when EF is greater, we have it as overexcited, which is a lagging power factor, and when it is underexcited, it creates a leading power factor. So underexcited or overexcited corresponds to the projection of EF onto VT. If it is greater, it is overexcited. If it is lesser, it is underexcited. Same thing here. If the projection is greater, overexcited. If the projection here is lesser, it is underexcited. But for motoring, overexcited means a leading power factor, while for generating it means a lagging power factor, right? So this is one of the tricky things that you have to keep track of, that you have to understand properly. It has nothing to do with the generating and motoring option. Modes have nothing to do with the size of EF. It has nothing to do with the overexcitation or underexcitation. It has to do with the polarity of the power angle. So let's come to torque now. Torque again is simply power over omega, power over the speed. So we have our equation for power. We simply divide it by the speed, and we'll see that we have this sine delta in it. The speed here does not vary, it's the synchronous speed. So if I plot this, I will get this 1/2 of a sine wave, and it will reach maximum torque. This is constant, this is constant, this is constant, this is constant. It will reach maximum torque when sine delta is maximum, which is at 90 degrees. So the maximum torque is achieved when you have this 90-degree phase shift between the flux from the mechanical side and the flux from the electrical side. Good. After that, the flux starts to slip down again. And I don't take slip in the sense of the induction motor slip. It means that I'm just talking about this. It starts to reduce. So that is the torque. Here, notice we plot torque with load angle, with the power angle. we don't plot torque with speed simply because this is a synchronous machine and it operates at synchronous speed, so the torque does not vary with the speed. So the torque speed graph will simply be constant. One of the problems we have, this is basically the end of what we have to learn. This is so just for some extra information. For heavily loaded motors, one of the problems we have is when you start the machine, you're not starting from synchronous speed. So how is it going to operate? Sometimes the magnetic field does not have enough, you cannot produce enough torque to start moving the load. So you need to come up with some sort of starting circuit to get enough torque to bring the machine up to synchronous speed so that it can operate as a synchronous generator. So the most common way of doing this is to install damper windings, and we'll see that this is basically makes the machine as an induction machine for the low speeds. So if we look at it, we'll see that these are the damper windings here, right? Remember, your machine will be around here in the stator. And if you think about a squirrel cage induction machine, this is what a squirrel cage machine was. You had the rotor bars here, and then they were all shorted together on each side, right? So it is exactly the same thing. So what happens is, when you are starting, you induce a current. It works exactly like an induction machine. You induce a current into the damper windings. That creates a current in them, and those currents now create their own magnetic field, which interacts with the stator magnetic field, and that allows a torque to build up in exactly the same way as an induction machine. It actually is an induction machine for these early speeds. And then as the torque starts building up, when it reaches near to that synchronous speed, remember the induction machine at full load gets, the slip is very, very small. In the examples we looked at, 2 or 3%. So it's 97, 98% of synchronous speed. Then you have the synchronous speed is close enough, the torque, there's sufficient torque that the stator field will latch on to the rotor field, and it will begin moving at synchronous speed. And once that happens, so you give it that initial push and it starts moving at synchronous speed, then what happens to the damper windings? If you have the system moving at synchronous speed, then you have no relative motion in the conductors, no induced EMF, no current flowing, and the induction motor effect goes totally to zero. So there will be no effect from that, and you don't have to model it in any way. So this is just a way to get the machine up and running so that it could operate as a synchronous machine. So let's look at one example here. Actually, what I think I'll do, because the video is quite long now, is I'll stop it here and I will treat with this example in a separate video. So I'll stop here.